Hey class, congratulations, you did it. The exam's over, and now it's time to let good times roll. We'll finish up with chapter 10, which is graphs, and then we will move on to chapter 11, which is trees, and that is a really short chapter. So I'm going to run through all of the definitions and theorems that come from that chapter, and then we will spend a fair amount of time working on the algorithms and translating them from pseudocode into actual code. And this is October 1st, and after today we will have finished all of the principal material for the course. So most of the rest of the time will be spent reinforcing what we've already learned, building up our understanding of the algorithms that come from the material that we've already covered as far as recursion goes. And as you'll see, there are methods for spanning trees, implementing spanning trees, and tree traversal algorithms, and then the data structures that are built on top of these, such as AVL trees and heaps and so forth. But we're done, after today with that principal material. Chapter 12 is a chapter on Boolean Algebra, and chapter 13 is on modeling computation. So I didn't cover those in depth last year. I don't think I covered chapter 13 at all, and I don't believe any of the other course sections are either. So I'll go through and I'll cherry pick, and if there's something that I really would like to cover with you, then I'll go over it. But if not, well, you're not getting tested over it, and there's no homework assignments on it, so nothing really to worry. So we'll run through the notes that I have for trees and graphs, and then we'll spend some time implementing whatever algorithm is there, and then that'll be basically the time for the next 3 weeks is going through and implementing the algorithms and trying to find these real world examples that will sort of help you along your way as you become software developers. And then the last third of the semester, so November and that time following the exam on October 27th, we'll spend that time learning how to prove things, basically. So you've already done proofs by induction, which is great, but there are other methods, and proving things in general is extremely difficult, or at least I found it to be. So I think it's worth spending a little bit of time on that and just building up your tool set as you learn to work on those types of problems. And that's it. I mean, today is basically it. It's the semester continues, and I've kind of taken this course of action where we've just done kind of the high level run through of it all, so that you're at least introduced to it. And I want to live what I preach, that the 80-20 rule, so you can get the bulk of you can get the gist of things done pretty quickly in 20% of the time, right? 80% of the work in 20% of the time, and then you end up having to put a lot more effort to get the rest of it. So it's not exactly 20% of the time, it's the first third of the class that we will have spent on going over all of the chapters that we're going to cover. But we'll run back through and we'll do that deeper dive, and it's a lot more work, but I believe will provide you with a solid foundation going forward. So this is the last not really programming intensive day, and I say that, and we're going to end the class spending a fair amount of time programming, but whatever. So let's finish up the notes, and then we will feel our way through this semester, and I will try to come up with homeworks that are both challenging and not necessarily terribly programming intensive. But at the same time, I really want to emphasize that there is a point that you can get to where the barrier to entry for a software development problem is no longer getting your code to compile or having it look like whatever the prescribed data structure is, or whatever. Like at some point the actual coding becomes fairly a familiar task, and it's just labor, it's just work that you go through. And so while I have you for another couple of months, I want to make sure that we put in some time to try and get to that point, or at least edge our way closer to it. Um, so that as you go forward, maybe some of these challenges aren't as intimidating. So that's my goal. So I'm really excited that we're at this point, and we'll carry forward. Okay. Okay, so we ended with Dijkstra's algorithm, which covers finding the shortest path between any two vertices in a graph. And I uploaded the JavaScript for that, so you can run it using Node. For those of you that haven't installed it, I would definitely recommend installing it at some point. You can get there just by going searching for Node, right? Download, whatever, it'll take you there. So the current version is 12.18. Okay, so quick note, LTS is long-term service, so it means that if you install this version, that it'll be supported for a while, which is important if you're doing something for a company, like company software development. But sometimes you can get a little more bleeding edge stuff if you go to the current version, right? So this is version 14. It's up to you. I don't want to tell you that what you're doing isn't important, but you're not looking for long-term service. You're looking for the features that'll be there whenever you finally graduate. So if you want to go with the current version, that's fine. For most of the stuff that you'll be working with, there is no difference. So just want to alert you to that. Okay, so yeah, install that. You can run the Dijkstra application that I gave you. Yeah, we'll discuss programming more later on. Traveling salesperson problem, visiting in cities. So you have in vertices, you want to visit each one once, and every vertex connects to every other vertex, making it really difficult, giving you a lot of options. So there's in order to visit every path, in order to visit every city or vertex or whatever, regardless of where you start and then end up back where you started, there's going to be in factorial, in this setup, in factorial paths, where n is again the number of vertices. So it grows at a rate, it's exponential growth, but it's factorial growth, which is exhibits logarithmic concavity in terms of its growth. So it's even faster than something exponential, right? Then it's even faster, or it grows even faster than e to the x, which for a computer scientist is terrible news. It means that that's an extremely difficult problem. So I mentioned it in passing. I'm sure we'll come back to it and discuss it later. But just an introduction to what the problem is. Okay, planar graphs. So a graph is called planar if it can be drawn in the plane without any edges crossing. Let me give you an example, right? Such a drawing is called a planar representation of the graph. So, hold on. Okay, so it's pretty simple. So if you have something like that, that's planar. The vertices, everything's connected. You can get to anywhere, however you want. But as you start adding vertices, then you can run into trouble. So okay, we still don't have any vertices crossing. We still haven't had to have any vertices crossing. Okay, we're still good. So this one is connected to every other node, right? So it's connected to B, C, D, and E. C is connected to A, E, D. Right? D is connected to A, B, C, and E, and then E is connected to A, B, C, and D. So, but these two are not connected, and there's no way to connect them without crossing over one of the previous edges. Right? So that one, that proposed edge running from here to here, would cross over the edge that connects A to D. If we were to try the loop trick again, then we would cross over the edge connecting A to E. So once you get to 5 vertices, it's not possible to have it complete, where every vertex is connected to every other vertex, and still draw it in a planar method. It's where you can draw it 2 dimensionals and you can arrange it and connect all the vertices, all of the adjacent vertices with edges, without having any of the edges cross over. So that's planar. And so again, once you get to 5 vertices, you can't do that. You can't have a complete graph anymore and still have it be planar. So that's the definition. That's what we're talking about here. Okay. Let's see. Planar graph, planar representation of graph can splits into regions, including an unbounded region, right? Okay. So, yeah. Here, let's jump back to the graph. Okay. So, getting rid of the regions, or the vertices that don't conform to our requirement. Right, so everything is connected except for C and B here. Then the regions that we're talking about are these spaces in between. Okay, so it's just the areas that if you had a connect the dots game, right? Like you go to a restaurant, they give the kids these connect the dots things, and then they connect the dots, right? Where the dots are just the vertices, and then it's a picture, right? You color in the picture. So all this is saying is that you would color in all of these different regions, right? So you have the sky, right? The part that isn't contained within any of the other vertices. It's the unbounded region. And then there's your princess or whatever it is that they've connected the dots and made, and so you have all of these other regions, right? Okay. So then so those are definitions. We finally have a theorem. Let G be a connected planar simple graph with edges E and vertices V. So remember, graphs are composed of edges and vertices, or vertices and edges. Let R be the number of regions in a planar graph representation of G. And then R is equal to E minus V plus 2, right? Okay, so what did we just say? So the number of areas for my kids to color in whenever they go and they play connect the dots and then color in the image afterwards. So the number of different areas that they can color, or colorable opportunities, is R in this case, and it's the number of edges minus the number of vertices plus 2. Okay, so if we have one vertex and 0 edges, then this is 0 and this is 1, so 0 minus 1 becomes negative 1, plus 2 is 1. So we have a dot, and then we're coloring in everything else. So in the example of my princesses and their castles, is that in this case it's sky, right? Like the only region is sky. And the same thing, it's still true that if we have 2 vertices and 1 edge connecting them, so this is 1 minus 2, so again we have negative 1, and then we add 2. Well, that's just 2 dots connected by a line. So we would have, something that looks like a bird in the distance or whatever. It's just this line, and it's still all sky, right? Like we haven't actually enclosed any area that my kids can color in. But the formula holds as we go forward. So as we add vertices, so from there, as we add vertices and then we connect them with edges, we start to get colorable regions, like additional colorable regions. The formula is pretty straightforward. It's this, right? It's the number of edges minus the number of vertices plus 2. And that's how many different places my kids look to color whenever they're playing Connect the Dots. Okay, so then corollary, if G is a connected planar simple graph with E edges and V vertices, where we have at least 3 vertices, then in order to hold this requirement that it's connected, planar, simple, right, then we have this new restriction. So if we have more than at least 3 vertices, then in order to hold this property, connected, planar, and simple, we can have no more than 3 times the number of vertices minus 6 edges, right? So it's an upper bound. And I just showed you that once you get to 5 vertices, you're no longer allowed to connect everything. You can't have this complete graph because it's just too many edges, and you lose the planar property in that case. And so you can you could also keep the planar property by violating it if you made it not connected, right? But in order to have all of this, right, connected, planar, and simple, right, simple where no more than one edge connects 2 vertices, right, then this is your restriction, right? So okay, another corollary. If G is a connected planar simple graph, then G has a vertex of degree not exceeding 5. And again, it's the same thing. So you can't have that planar property if you allow too many edges. So you just get to a point where, you can't, you apparently can't have more than 5 edges sprouting off of a single vertex if you want to maintain that planar property. And another corollary, if a connected planar simple graph has E edges and V vertices, where we have at least 3 vertices and no circuits of length 3, then our edges are restricted to 2 times the number of vertices minus 4. So we can have even fewer edges than up here. Right? Okay. Alright, back to definitions. So if a graph is planar, so it will be any graph obtained by removing an edge UV and adding a new vertex W with edges UV and WV. Such an operation is called an elementary subdivision. Okay, so this is going to be easier if I just show you. Okay, so what did we just say, right? So we're saying that we're removing and then we're adding to or whatever, but I find it easier to just consider, well, we're adding just a point somewhere in between on that edge, right? So as far as telling the computer what we're doing, we're removing an edge and we're adding 2 new ones where it runs, from here to here now instead of running all the way here, and then from here to here, right? So we've added some midpoint and we're calling it W, right? So that's an elementary subdivision. It's exactly what you think, right? So if you were considering network cable or something like that, then what it means is you've cut the cable, you've crimped it, you've added new terminal points to it, and then you have some repeater or some signal booster or something in between. So nothing has changed. The topology of the graph is exactly the same, except that the edges now are a little bit shorter in one location, right? So you've taken it, you split it, you probably boosted the signal. The structure is all basically the same, but you've changed it just a little bit with this elementary subdivision, right? And that just means that you've kind of split one of the edges in, not necessarily in half, but you can think of it as being in half. Okay, so now we have another definition, homeomorphic, right? And so this is a term that has a concept in topology in mathematics, and it's just essentially it says that, well, you're dealing with basically the same thing, and here, let me show you, right? So that's all it is, right? Formally, if we have two graphs, graph 1 and graph 2, and this one has the set of vertices 1 and edges 1, and the set of vertices 2 and set of edges 2, then they're homeomorphic if they can be obtained from the same graph by a sequence of elementary subdivisions. Okay, so again, if you think of the network, right, like the internet, then just by simple maintenance, right, like, okay, so we're running fiber optic cable from Dallas to St. Louis. We discovered that there was a point somewhere in between where the signal is broken, so we've cut the cable, we've replaced it. For cost reasons, we only wanted to replace the minimal amount of cable length, so we cut that part out. We've replaced it with a new cable, and we've added 2 new terminal endpoints or whatever, right? However many. And so nothing really changed. We didn't really add any new data centers. We didn't add any new internet service providers. All we did was fix this broken link by replacing it with 2 other links. And so that it's still essentially the same graph, but now we have additional vertices to consider, and because of those vertices and the fact that they lie along the path of what used to be a single edge, we now have some additional edges. Like we've split the cable in 2, basically, where it used to be 1, now it's 2. But it's still basically the same thing. And our term for, well, it's basically the same thing, is that those graphs are homeomorphic, right? So fancy word for a simple concept. Okay, so theorem. A graph is non-planar if and only if it contains a subgraph homeomorphic to K33, and this is the bipartite example that we looked at earlier, or actually I don't think we did exactly that one, but I'll show you what it is. Or K5. So K5 is the star topology or whatever. I'll just show you that one as well, right? But it's what we've been talking about with this other graph. So it's the complete graph with 5 vertices resembling a 5-pointed star, and K33 is the bipartite graph. So let me just draw those for you real quick. Okay, so the first one's K33. And then the other one's K5. Okay, so yeah, you can see, like, the way we've drawn it, obviously there's a lot of edges. If you want to play with it, these are, according to this theorem, these are the only 2 you need to consider. So, take some time, draw it out on a sheet of paper, and try, to draw something that is, even stronger than homeomorphic, right? Something that is isomorphic to these, right? So you can rearrange them on the page, but, go ahead and keep the labels, right? So here we have ABC and alpha, beta, gamma, right, for K through 3. And so A connects to each of the Greeks, B connects to each of the Greeks, and C connects to each of the Greeks. But none of the Latin letters connect to themselves. Right? In K5, each vertex is connected to every other vertex. So take a little time, convince yourself, try and draw it on a page where each of the edges connects to its appropriate vertices, and try and draw it so that none of the vertices cross over each other. And what this theorem is saying is that you can't. And more important than that, is that these are the fundamental violations of that planar requirement or condition, so that anything that violates the property of being a planar simple graph, it contains something that looks like this, right? There's some structure. It's either this one or this one that violates, or possibly both, that violates that condition in order to prevent a graph from being planar. And so I think it's kind of cool that it breaks down, that it simplifies to just two cases. I think that's pretty phenomenal. Usually you would see that there's some primality, something to do with prime numbers or whatever that is preventing it or whatever. But in this case, there's two. So I think that's kind of cool. So yeah, play around with it, whatever. But that's what the theory is saying. Okay, so graph coloring. I had originally intended to skip this section, but the fact that we're running through our material, I thought, well, okay, whatever, we'll include it. It's but more than that, right? It's more than just filler. I read through it, and it has a concept, and I want to include as many concepts as possible, just different ways of considering a problem that'll allow you to translate whatever you run into as you're working through whatever problem you're working on, to translate it into something that you studied as an undergrad, and equally important, something that you can devise an algorithm to handle. We will spend 3 minutes on graph coloring. Okay, so a dual graph is a planar graph constructed from the regions of a planar map. And so again, this is the connect the dots and then color it, right? That's the planar regions. The regions of the map become the vertices of the graph. Two regions are considered adjacent. Okay. So yeah, this is going back and forth between a map, like the geographical maps, like the map of a country, and a graph representation of that map. So two regions are considered adjacent and connected by an edge if they share a border of length greater than 0. And so the four corners of Utah, Colorado, Mexico, and Arizona in the United States is a perfect example that two regions are not considered adjacent if they connect only at a point. So New Mexico, in that example, would not be considered adjacent to Utah because they only touch at a point. Like they have to have a non-zero length border. And in that same regard, Arizona is not considered adjacent to Colorado. So that's the restriction. But this says, the dual graph says that you can jump back and forth between the two. So you can have a graph in the computer science sense with vertices and edges, where in this case each of the states would represent a vertex, and then their borders would determine the edges. So if the states share a border, and not in the New Mexico-Utah sense, then you can draw an edge connecting them, right? And so it makes sense that because the map is itself planar, it's something that readily fits itself onto a sheet of paper. Then the graph that's associated with it, that you construct in the same manner, would also be planar, right? And so this is is just a concept, a way to translate something that doesn't look like vertices and edges into something that is vertices and edges. And so that association is the dual graph. Right? Okay, so the coloring of a simple graph is the assignment of a color to each vertex of the graph so that no two adjacent vertices are assigned the same color. Okay, so this is, you can think of coloring the vertex, but vertices are just a point, and so it, the vertex could have a color if you had the graph representation, but if you were using the map representation, then you would be coloring the region occupied by the state. So the chromatic number of a graph is the least number of colors needed for a coloring of this graph. So where we have this restriction that vertices joined by an edge, so adjacent vertices, cannot have the same color. So Texas and Oklahoma would not be colored the same because they would blend into each other. So if you were coloring the map, you would have to use distinct colors. And so the chromatic number is just, well, what's the minimum number of colors that you can use to satisfy this condition, this definition of coloring, for a given map. And so what's the minimum? So you could always do it where each vertex gets its own color, but that's not interesting. We're not going to name anything after that. So it's the minimum number that we're concerned with. The chromatic number of a planar graph is no greater than 4. That should actually be a theorem, I think. Yeah, that's a theorem. I'll correct that. But the chromatic number planar graph is no greater than 4, which means that you could color any map using no more than 4 colors if you followed this coloring rule. Not saying it's going to be intuitive which vertex gets which color, but this theorem says that that's the case. Okay, so great. That's a cool little curiosity. If I go back into world geography, and now I know that I really only need 4 map colors, but is there anything else we can use? So this was the reason that I included this concept in here. So how could we use this, right? How could final exams at a university be scheduled so that no student has 2 exams at the same time? And so the answer is that you would model the problem by defining the courses to be the vertices, and then courses would be considered adjacent or connected or have an edge drawn between them if there's at least one student in common between the 2 courses. And then the colors would represent the time slots themselves. And so the first thing you'll notice is that we're no longer discussing planar graphs at this point because there's just too many edges. The students take too many vertices, and they're going to cross over. And so so we're dealing with coloring here, right? So we're no longer dealing with simple planar. It's just a simple graph, right? And so the chromatic number goes up now, but it's just a different way of tallying it. So instead of assigning letters or whatever, we're now assigning colors. And if in the spare time that we go over as we discuss other proofs or ways to approach problems, color is a very effective means of conveying information and distinct information, and so I thought this was an interesting way to approach the problem. So we've defined it so that we have this new concept of adjacency, and then we can just count something else, and in this case we're counting the number of distinct colors. Okay. Trees. Okay, so trees are used to represent hierarchical structures, such as the organization of charts that a business might use to represent the chain of command. But we could also use it to represent executive structure within the government. So each individual has someone that they report to, and this goes all the way up to the chief executive. Okay. Introduction of trees. That's the same. I guess the same would be true of the old monarchy style as well, right? It all stops with the king in that case, or the queen. Okay. So we define a tree. It's a particular type of graph, and it's named because it resembles an inverted tree or a family tree, right? Or I guess a family tree would be named after this structure. It is a connected, undirected graph with no simple circuits, right? And basically, we achieve that by having that rule that you can have familial connections going up, right? Like each node, it's possible to have a parent, and it's possible to have children, but it's not possible to have. Well, alrighty, we're like violating the family tree structure or whatever, right? It's not possible to have two parents, right? But in the case of a programming tree, no, it's not possible to have two parent nodes, right? And so in a family tree, I guess the parent would be a coupling or whatever. But okay, and typos. Okay, an undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. Okay, and so this is just going in the other way, right? So we defined a tree as a particular type of graph that doesn't have simple circuits. And now we say, well, a graph is actually a tree if it satisfies this condition, right? Okay, so then a rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. It's called an M-ary tree if every internal vertex has no more than m children, right? So earlier in the semester, I'd said that we could use file systems to represent, or tree structures to represent a file system. And so a file system is an example of a tree that is not an M-ary tree. We don't necessarily cap the number of directories that a given, well, I mean, we kind of do, but for the sake of this argument, we don't, right? There's, 16,000 or whatever that limit isn't really, what we're discussing here, right? So we're typically talking about like a binary tree or a ternary tree where there's a hard cap on the number of children that you can have in the tree for any given node. So if it's 2, it's binary. If it's 3, it's ternary. If it's 4, then it's 4-ary. If it's 5, it's 5-ary. Right? Okay, so you can have no more than that number of children. The tree is called full, or a full M-ary tree, like a full 5-ary tree, if they can have 5. If every internal vertex, so everything that isn't a leaf node, has exactly m children. An M-ary tree with m equals 2 is called a binary tree. Okay. So it's full if it is either a leaf node or, in the case of 2, if it has 2 children, right? So it's one or the other. That's a full tree. Okay, another definition. An ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. Typically, they are drawn in ascending order from left to right. Okay, so this condition will come back whenever we discuss priority queues and heaps and AVL trees. So it has special meaning, and basically it means that the tree itself is a data structure that's designed to provide some guarantees on order. So there are, whenever you're working, whenever you start programming, if you have a data structure and you want to maintain order, like eventually you're going to loop through it, and you don't want to have to pay the cost of sorting it whenever you loop through it, you want to loop through it in order, and you want to maintain it always in that given order. Then you're going to use something like a sorted set or a sorted dictionary or whatever. And then internally, so the implementation will be hidden from you, but it'll be maintained using something, either a priority key or an AVL tree or something. And so that something, that method of keeping it sorted with a tree is going to be in general called an ordered rooted tree. Okay, more terminology. So the nodes of a tree are going to be, there's the root, which is root, there's the internal or interior nodes, and then there are the leaf nodes. And so the root is obviously if you're doing anything recursively or whatever, this is your halting condition. The interior means that it is not root, typically. Root could be considered to be an interior node, but it's special enough to get its own designation. But it means that it has children. Right? And so in the case of an HTML document, the root would be the document itself. Right? And then the internal nodes would be all of the HTML tags, right? Like HTML, head, body, div, paragraph, or whatever. And then the leaf nodes are going to be all of the text. So the actual Ascii characters are UTF-8 characters themselves. And so these have some other meaning, right? Like it's just an intuition for what these are conveying, right? So there's those three classifications. Okay. In a binary tree, if an internal vertex has two children, the first child is called the left child, and the second child is called the right child. And it's because of the way we draw it, right? So as you're descending the tree, you get to choose left or right. Okay. The subtree rooted at the left child is called the left subtree, and the one at the right child is called the right subtree. Okay. So we'll come back into this definitely whenever we discuss AVL trees, which I'm leaning towards next time doing that. So we will come back and discuss this further. Okay. Yeah, this is a good example. So saturated hydrocarbons, or any molecular structure without double bonds, right, only single bonds, can be represented using a tree structure. So you would start at any end, and then they would have, their bonds would represent. So in the case of this, right, the carbon atoms would all be the interior ones. You would choose one carbon atom to be the root, and then there are four chemical bonds. It's always bonded to four other elements, or there are four bonds available. Sometimes it's double bonded, but in this case it's saturated, right? So there are no double bonds. So then the hydrogen atoms would be the leaf nodes because they only connect once, and then all of the other carbon atoms would be interior nodes. And so if it's saturated, then it looks like a linked list as well, but that's not necessarily the case. The carbon can branch and create something that does look a little more like a tree structure. So okay, so that's a organic chemistry example. The organization chart for a company with a chief executive officer or a chairman of the board of directors may be represented as a tree structure, and a computer's file system may be represented as a tree structure. Okay, so we have a theory. If we have n vertices, then there are n-1 edges, and you can prove this inductively, right? So if we have just a root node, so one vertex, then there are 0 edges. Holds true. If we add a child to the root, then it is connected, obviously, to the parent node, to the root. And so we have 1 edge. So 2 vertices, 1 edge. If we add another child, it doesn't matter if we add it to the root or the one that's a child of root, it's still going to be connected by 1 more edge. And so we start with root, we start with 1 vertex, and then every addition adds 1 vertex and 1 edge, so that this property always holds. Okay. A full M-area tree with I internal vertices contains n equals mi plus 1 vertices. Okay. So this says that if we are given the number of internal vertices and we're given the property that it's a full tree with m children for every node, right? So we're given the internal vertices. Then the total count is n equals m times I, right? Where I is our number of internal vertices, m is the number of children per node, plus 1. Okay. Another theorem. Full M-area tree with n vertices, and there are I internal vertices, computed this way, and L leaves, where the number of leaves is computed this way, right? And again, M it's 2 if it's binary, it's 3 if it's ternary, it's 4 if it's four-ary, 5 if it's five-ary, right? So it's just the number of children, right? And again, we're dealing with the special case that it's a full tree, that everything is either an interior node or a leaf node. Okay. So here we have a way to compute I and L. So internal or interior and leaf from the number of vertices and the property of the tree, right? The number of children at each interior node. Here we're computing the number of vertices from the m, the number of children, right? And I, the number of interior nodes, and here we're computing L from m and I. Here we're computing the number of vertices overall from m and the number of leaf nodes, and we can compute I, the number of interior nodes, from the number of leaf nodes, and the mness of the tree, right? And so it just shows that you can, that given enough information, you can find, one of the remaining properties. And so, but that's only if the tree is full. But you can also use full trees to represent upper bounds on trees of a given height. So, so even if you don't have a full tree, you can still make use of this information to define upper bounds on the amount of data that you're dealing with. Okay, so the level of a vertex in a rooted tree is the length of the unique path from the root to this vertex. Okay, so this will be cleared up with just a quick representation. Okay, so okay, so here we have root, right? Okay, so it's just the distance, the number of edges from the root. So the root is 0 distance from itself, so it's at level 0. And in computer science, we index with 0 as as was intended by the laws of nature. We should be indexing at 0, but whatever. Okay. So level 1 means that you are 1 edge distance from the root. Level 2 means that you are 2 edges, so you're a grandchild of root, and so forth, right? So as you draw it out, you should be drawing your trees so that you have it arranged in levels, and that's the most intuitive way to see the tree. But that's all we're saying is the number of edges that you have to count back to get to root and then root is itself 0 distance or level 0. And so we're about to define height, and that is intimately related to level. Okay, so the height of a rooted tree is the maximum level of the set of leaf nodes. In other words, the height of a rooted tree is the length of the longest path from the root to any vertex. Okay, so jumping back to our example. Okay, so most of the nodes, yeah, a fair number of the nodes are up here, right? So the tree isn't really, for the most part, all that tall or all that deep, but that's not how we define this, right? So actually can't quite see. So this tree has height 5 because the longest path to get back to the root is right here, and that's the leaf node at level 5. So that's how we define height. It's not some average or any other property. As well, okay, well, what is it in the worst case? And so that's the height. Okay. Another definition, a rooted M-ary tree of height h is balanced if all leaves are at levels h or h minus 1. Okay, so balanced is different than full, but it's as close as you can get to full. So there's right. So if you have a binary tree with of height 1, then it's a root with 2 children, right? A left child and a right child. If you have a full binary tree of height 2, then you have 4 children. So the left child of root has 2 children itself, and the right child has 2 children itself. And so it's full. But what if you only had 3 nodes at level 2, right? So you just didn't have enough data to make it a full tree. Well, it's balanced if it's balanced in this case. Here, let me show you. So here, the height of the tree is 2, and you have this one that that is at level L minus 1, right? But that's not a leaf node, it's an interior node, so it kind of obscures what we're talking about. But this would still be balanced, right? So you have the leaf nodes over here, and you have this one that's waiting to become an interior node, but there's just not enough vertices to make a full tree. But it's balanced because it's making that good faith effort to be a full tree. It's balanced just means that it's as close as can be to full, but there's not enough vertices, right? Okay. Alright, so now we have a theorem. There are at most m to the h leaves in any M-ary tree of height h. So again, I think this is something that becomes intuitive and something that you can remember the theorem if you put in a little work now, right? So the maximal number of leaf nodes happens whenever the tree is full for a given height. So you have the most number of leaf nodes if you're taking advantage of all of the slots available to you at height h, right, or level h. And so that's when it's maximal, right? So that's this at most part. The m to the h is again, you can get there recursively, right? So if you have a binary tree and you have height 1, then it's the root node with 2 children, right? So it's 2 leaf nodes and 2 to the 1 here. If you take each leaf node and you give it 2 children, right? So you've increased the height by 1, then you've doubled the number. In the case of a binary tree, you will have, for each one, you split it into 2 children, right? Then you will have doubled the number of leaf nodes. So then at this point, you would have 2. So by increasing the level to h plus 1, you went from 2 to the h to 2 to the h plus 1, right, for a height of h plus 1. So this is a recursive sense. And that holds true whether you're dealing with 3 children in a 3-array tree or 4 children in a 4-array tree. And so it's this exponential relationship where you have the number of children, the restriction on the number of children, to the power of whatever the height of that tree is. And so this also jumps right into, well, then the height is an upper bound, right, for the log of the number of leaf nodes. So if the number of leaves is maximal for that height at m to the h, then taking the log of this would give you, with base m, so in the case of a binary tree, m is 2, means that the height is at least the log, the ceiling for the log of the number of leaf nodes base 2. Right? So these two are basically the same thing. It's just here you take the log of this. Right? Okay. So applications of trees. So in addition to being a useful representation of hierarchy, like in a file system or family trees or whatever, we can use it with additional properties and restrictions, and we will in the next class, to order the data in a particular way. And so a binary search tree is one example of an application. Is a binary tree in which each child of a vertex is designated as a right or left child. No vertex has more than one right child or left child, and each vertex is labeled with a key, which is itself the embodiment of the item, yada yada yada. Okay, so what am I saying here? Okay, again, this would be easily represented if we just take a look. Okay, so I'm going to draw 2 examples, and I'll show why the basic binary search tree isn't enough to really be useful. But first, I'll show you kind of how it breaks down. Okay, so this is kind of some optimal example for the in-order traversal of a binary search tree. Okay, so you see that it's perfectly balanced. We have a full tree, which is what you want if you can get it, right? And if you can't get a full tree, then you want a balanced tree. But we have a full tree, which is nice. And it has the property that every vertex, or the letter, whatever, but we'll use vertex and value of that vertex interchangeably when we discuss this. To the left of this root node is in some sense less than the value of this node itself, right? So what that means in terms of alphabetic sorting or lexicographic ordering is that everything over here comes in dictionary order before this value, right? And everything to the right of it comes after. Okay, so that's the property of binary search trees. Let me show you another binary search tree that highlights the problem. Okay, so if we're looking for, some value, right? Like if we're looking for G, right, or we'll say E, right? Then in this one, we would do a comparison, right? We would see that E comes after E comes after D, and we would come down to F. We would see that E comes before F, and then we would go to the left, and we would find our item. And we would do it in log of n operations, where n is the number of vertices, the number of words in our dictionary, the number of letters in our tree or whatever. And so this also satisfies the property of a binary search tree, where everything to the right of the root node comes after it. But it looks a lot like a linked list. We've just kind of drawn it at an angle. It is not doing a whole lot of good for us, right? So in order to find E, we're not doing log of n operation, or not log of n operations. We're doing something that's starting to look a lot more like a linear search, right? Because it's just a linked list. So how is this any better than a linked list? We've just kind of glorified our linked list here. So to get a little more bang for our buck, we need to find a way that as we're inserting, that we're balancing our tree, that we're doing some additional actions, so that we don't end up like this. We don't rely on chance or the ordering of it, right? So if you were to do the straightforward insertions as you get the items, then if the items are already inserted or if they're already sorted when they're given to you, then the successive insertions will give you something that looks a lot like a linked list. But it seems like you should be able to do a little bit better if you're given the items sorted, right? Like in the case of binary search, if we have it sorted, then we can already find our items in log n time. So how is it whenever we move it to some structure that's supposed to maintain that property, that's supposed to give it to us automatically, that we've gone from a logarithmic search time to something that's linear? We've made the problem worse by optimizing it, right? So what can we do to improve on that? That's something that we'll get into next time whenever we look at AVL trees. But let's continue on. We'll finish the definitions, we'll finish the theorems, then we'll do all of the coding next time, and then following the next exam, we'll dive into proofs. And I want to spend the next 2 semesters, or not, sorry, the next 2 months discussing, programming, yes, and proving, yes, but additionally data visualization, which is whenever I try to break down a really complicated problem, the first thing that I have to do is find some way to visualize it, some way to imagine the problem that kind of gives something to grab onto and sort of just like peel away at the problem a little bit. And so data visualization is absolutely critical for that. But we'll come back to that. Okay, let's carry on with trees. Okay, so that's binary search tree. We'll discuss that in a little more detail. We'll add some implementations for next time. Decision tree. Okay, so we can also consider the execution of a program, right, which has branch points and flow control structures as a decision tree. So if this condition, run this loop again. If this happens, then run this statement, else run this statement, and so on and so forth. And so it's a series of tests and then a branch, right? So you either go left or go right depending on whatever the evaluation is. So if it's equal, then do left. If not, do right. And so representing the program in that manner is called a decision tree. It's, or you can read it as it's written here, but essentially that's what we're doing for, right? The abstracted execution path of a program or procedure may be represented using a decision tree. Okay. Theorem. Sorting algorithm based on binary comparisons requires at least log, or the ceiling of log n factorial base 2 comparisons. And so we proved that already because the number of leaf nodes, you proved that in your homework. The number of leaf nodes for final states of a program was equal to the number of permutations, or of a sorting program, was equal to the number of permutations on the size of the set being sorted, which is n factorial. And so the decision tree, the comparisons, if A is less than B, do nothing, otherwise swap, those are the interior vertices of, or the branch points of your program, and then the final states, the result, is the leaf nodes, and so you guys have already proved this in your homework. Okay, corollary, the number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is best worst case n log n, right? So yeah. Okay, so it's basically the same thing. So because this works out to n log n, and that was really the result of the arithmetic that we did, where we changed this into n times n minus 1 times n minus 2 and so forth, and then we used the multiplication within the log to be addition outside of the log, and then all of the simplifying arithmetic. We arrived at n log n. Okay, and then theorem, the average number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is n log n. Okay. Then traversing a tree, so navigating a tree, looking for a file within a file system, looking for text within an HTML document, so forth. You're going to have to use tree traversal. So the procedures for systematically visiting every vertex of an ordered rooted tree are called traversal algorithms. In the case that you wanted to just print out what is in your binary search tree, you would need to be able to navigate the tree itself, and then write to the console and so forth. So there's 3 methods of visiting these nodes. There's pre-order, in-order, and post-order. Here, again, let me show you. Okay, so if we get rid of this, then, and we do a depth first search on the tree, then we would start here, and if there's a left child, we'll go left, and then if there's a right child that we haven't visited, then we go right, and then once we visited the children, then we return back to the parent, right? So it's a recursive implementation, right? So in pre-order, if the statement that we're executing is console.log or console.writeLine or system.out.println or cout or whatever, right? If all we're doing is just writing out the value of what's associated to this node, then that is our execution, right? That is what we're doing when we visit the node, is just writing out the value. And so pre-order, in-order, and post-order is where that comes as we're doing our depth first visiting. If it's in order, right, then we do it between the left and the right child. If it's pre-order, we do it before visiting any children, and if it's post-order, we do it after visiting the children, right? So in every case, right, we start here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So these are the different points where we could do a thing, right? That's where we will have either entered or returned to a given location, right? So we start at D, we check its left children. So in starting at D, we're at opportunity 0. We check the left child, which is opportunity 1. We check the left child, which is opportunity 2. There are no children, so we return, which is opportunity 3. We check the right child, it's opportunity 4. There are no children, so we return, which is opportunity 5. But we've already visited both the left and the right children, and then at our opportunity 5, right? So we return, that's opportunity 6. Now we visit the right child, because we've already visited the left child. That's opportunity 7. Right? We visit the left child first, right? That's what we're always doing, left, then right. So then that's opportunity 8. There are no children, so we return. That's opportunity 9. And then right child, that's opportunity 10. So there are no children, so we return. That's opportunity 11. And then we return, and that's opportunity 12. Okay, so you'll notice that for each of the leaf nodes, there's only one opportunity where it gets visited, right? For the parent nodes, or sorry, for the interior nodes, there's whenever we enter. So for the root, it's whenever the program first gets executed or the recursive algorithm is first called. For the interior nodes, it's whenever its parent calls it, right? Which, if you can't tell if it's a leaf node or not at first, so it's whenever it first enters, right? And then if it has children, there's another chance after it visits the left child, before it visits the right child, where it's that middle opportunity. And then once it returns from the right child, it's that trailing opportunity, right? And then, right, and so for all of the interior nodes, there were 3 opportunities, right? Whenever it first entered, whenever it came back from the left child, and then whenever it came back from the right child. And then for all of the leaf nodes, there was only one opportunity, right? So the difference between pre-order, in order, and post-order is pre-order, if we're writing to the console, then we do it whenever we first visit, right? So pre-order, we would write it at that first opportunity, right? We would be as greedy as possible as writing it to the screen. Right, so if you wanted, then you would take the opportunities, right? So each opportunity is associated to a vertex, right? And so for pre-order, you would take the very first opportunity to do your thing. In this case, to write it to the screen, right? And so it would be 0, 1, 2, 4, 7, 8, 10, right? You could just sort it, and you would know, right? And you could sort it, using the other opportunities as well, right? If it's in order, you can do the sorting as well. It's just for in order, you're selecting the middle opportunity. So after it comes back from the left child, but before it goes to the right child, right? Okay. So for in order, So we wait until the left child is done, but we act before we do anything with the right child. So then we're going down, right? And so we have A, and then we act before we visit the right child. So B, right, we're taking this middle opportunity. Right? C, and we return. The left child has returned, so we act on the root node before we visit the right subtree. D, and then and then so we do it for the left child, and then the middle, and then before we visit the right child, we print it out, right? So left child. Okay, so in this case, it was, full and balanced, and then it actually satisfied the in-order traversal, right? So that's how it was sorted. Right? So this was meant to be printed out in order fashion. Right? And then post-order, we take the last opportunity to do our thing, in this case to write it to the console. So again, we're doing depth first, right? Left, visiting the left, but we wait until both children have been handled, and then we feed ourselves in that case once we've already fed the children. That's post-order. Okay. So we come down, so we have A, and then we deal with the right child. C, and then we return, we take this last opportunity. B, and then now we deal with the right subtree for root. And then again we deal with the left child first. So E, and then the right child. And then the parent. And then we end on root. Again, as you're doing your depth first traversal, right, always going down the left path first, the interior nodes have 3 opportunities, and the leaf nodes only have the 1, basically. And so where you do your thing, like whether it's as soon as you enter, after the left child but before the right child, or after both children have been taken care of, that's the distinction between pre-order, in-order, and post-order. Okay. And so that was depth first, right? Each of those was an example of depth first, where we go all the way down to the deepest, the leftmost descendant, and then we work our way back up, visiting children in that order. Breadth first is where we do it level by level. So we do all of the nodes at level 0, which is the root node, and then all of the nodes at level 1, which is the first descendants of the root node, and then all of the nodes at level 2. And you'll implement that using a queue, and we'll actually do that. I'll give you an example next time if we have time. And then spanning tree is, well, graphs can have more than one, they don't necessarily convey to the concept of a parent structure, but you can kind of prune a graph. You can get rid of some edges, and as long as you keep it connected, and then you just get rid of all circuits, all subcircuits, or all subgraphs containing circuits. So you can actually get rid of enough edges to create a tree structure from a graph. And so that concept is called a spanning tree. And so you can induce a spanning tree using either breadth first or depth first. Right? So breadth first, in case of this, would be all of the nodes. So you just pick a starting node, and then all of the adjacent nodes would be visited first, and then all of the nodes adjacent to those that haven't been visited would be visited, and so forth. And in depth first, you just you pick a neighbor, and then you visit that neighbor, and then you pick a neighbor, and then you visit that neighbor, and so forth. And you do it in a recursive fashion, and then if you've already visited one, then you don't visit, right? So you keep this list of where you've already been, never going to the same place twice. And so if you use depth first, then you're probably not going to get a balanced tree if it's if there's a lot of edges on that graph. In particular, if it's a complete graph, then your depth first search will turn into something that looks a lot like a linked list instead of something that looks like a tree. But breadth first will give you a little bit more balance. But either way, either of those methods can be used to induce it, and we'll come back and we'll discuss this as well. So we have a theory. A simple graph is connected if and only if it has a spanning tree. And if you think about it, that makes sense, right? So if it doesn't have a spanning tree, then it meant that you found a place that you started and you visited neighbors, and there were just some vertices that you didn't get to, right? So if that's the case, then it wasn't connected. You had some stuff that was just dangling out there and wasn't connected to anything. Okay, so then the minimum spanning tree in a connected weighted graph is a spanning tree that has the smallest possible sum of weights of its edges. I have to verify whether or not this would be the theorem, but there are a couple of approaches to generate minimum spanning trees. So there's Prim's algorithm and Kruskall's algorithm, and and then we're to the background concept. So it's all algorithms and programming for the next 3 weeks, basically, until your exam, and there will be a couple of homework assignments in between. So we can discuss those next time. I will fill in the blanks as far as some of these algorithms go, and we'll spend some time on that. Graphs and trees are the most interesting in that regard, but I will show how we can use trees to address recursive recurrence relation, and we'll come up with some other examples for the other data structures. But now we have time to play around, so I'm super excited about the rest of the semester, that's it. That's basically it. You've made it to the end of the road. The rest is all it's more than filler. It's the part that you came for. But we've gone through our high level overview, and now we'll start cycling back and reinforcing what we've already covered. Okay, have a great weekend, everyone.